Hello, everyone. Let's start. Today we have a few different things to talk about. I'm going to continue and finish the linear algebra part. So we start with a short review. So we are going to have a short review of linear algebra. So I would start with a short review of linear algebra. And today we are going to continue with surfaces. They're quite interesting, exciting objects. So there's a part about surfaces which is in the book. I'm going to talk about that. And then there is a part about them which is not in the book, which is more related to topology. They've been just mentioned in the exercises. I'm going to talk about them too. Yeah, and that would be for today. Okay, so before starting, if there is any question, you can ask me. Okay, there is already one question. When should we have the homework to upload it to Blackboard by? Well, you should do it today, right? It's before Friday, if I'm correct. That would be my guess. It's fine even if you do it tomorrow. Okay, but be fast. Okay. And that's homework 2, not homework 3. Yeah, that is homework 2. Okay. So let's continue with lines and planes. So I would just do a very quick review, and then we would get to new things. Okay. So we talked about lines and planes, right? They are the important objects in geometry, in dimension, especially in dimension 2 and in dimension 3. So let's start our review with lines. Well, you know, if you're looking at lines in 2-dimensional space in R2, that's how they would look like. And any line is given by 2 points. Whenever you give me 2 points, there's exactly one line which passes through those 2 points. So for example, if I have 2 points, P and Q, there is exactly one line which goes through those 2 points. Now, if the coordinates of P are, say, x1, y1, and the coordinates of Q are, say, x2 and y2, the equation for this line is going to be like this. So we define m, the slope, to be y2 minus y1 over x2 minus x1. And if we do that, the equation for the line would be y minus y1 is equal to m times x minus x1. Right, that would be the equation of the line. The second step is to look at a line in 3-dimensional space, which I would show with a line in R3. Now, in 3-dimensional space, there are usually 2 ways to present a line. There are 2 common ways to do that. One is parametric equation. So in the parametric equation, we have a point, say P, and we have a direction, say V, and we are looking at the line which passes through P in direction of V. So it's like this. This is going to be our line. And it's parameterized. That's the reason we call it parametric equation, because it's parameterized by a variable which we showed by t. You can think about t as time variable. It's like at time t equals 0, you are at the point P. At time t equals 1, a particle, suppose you're a particle on this line, you have moved in direction of v for 1 second, and then you would be here at this point P prime. And for example, at time t equals to 2, you would be here at this P second. Or at t equals to -1, it means the place you have been at time t equals 0 would be somewhere like here, which I would show it with Q. The equation which describes this line can be written like this: x, y, and z, they are equal to, well, if the point P, it has the coordinates x1, y1, and z1, and the vector v has the coordinates a, b, c, the equation is x equals to x1 plus t times a, y1 plus t times b, and z is equal to z1 plus t times c. That's the parametric equation. Now we also mentioned another type of equation called symmetric equation. What is symmetric equation? Well, using the first equation, you can find t. T would be equal to x minus x1 over a. From the second equation, t would be equal to y minus y1 over b. And from the third equation, t would be z minus z1 over c. These make sense if a, b, and c are non-zero, right? Because all of these things are equal to t, they should be equal to each other, right? So x minus x1 over a is equal to y minus y1 over b is equal to z minus z1 over c. So what we have on the left side is the parametric equation. What we have on the right side is the symmetric equation. We have two kinds of equations for a line. Now, after lines, the next important thing in three-dimensional space is another geometric object. It's plane, right? So planes in, say, R3. So a plane is usually given by a point in a space and a direction normal to the plane, orthogonal to every line in the plane. So for example, if this is the point and this is the direction, the plane would be something like this, right? So if I have a point P and if I have a normal direction N, it gives me a plane which contains the point, and N is its normal vector. It's orthogonal to every vector in P. Every vector in the plane which contains P. So here, if the coordinates of P are x1, y1, z1, and the vector N is a, b, c, the equation for this plane is the set x, y, z, which satisfies this algebraic equation: a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. Okay, that's the equation of a plane. And the last thing we mentioned was how to find the angle between two planes. So I have one plane here, I have another plane here, right? There's an angle between them, theta, and I want to find this angle theta. So, and how can we find angle between planes? Now, the idea is that the angle between two planes is equal to the angle between their normal vectors. So if you have n1 and n2, one of them is the normal vector of the red one, so this is n1. And then we have n2, which is normal to the blue one. If we look at the angle between these two vectors, you would get theta again. And then using inner product, we know how to find the angle between two vectors. So that was the other thing we talked about. Okay. So the next topic I want to mention here and speak a little bit about that is about surfaces in three-dimensional space. So now let's start to speak about surfaces in three-dimensional space. Okay. Surfaces are kind of like planes. They are generalization of planes inside three-dimensional space, but the difference is that they are not necessarily flat, right? Planes are flat. They're just like a flat piece of paper. But surface means it can be non-flat, like a sphere, just the surface of sphere, not what you have inside, like a balloon, right? It's kind of curved. Surfaces can be curved. For example, if we look at a piece of paper, you can bend this piece of paper to get a cylinder. That's an example of a non-flat surface. So for example, one surface which we have seen before, it's sphere. You've seen sphere before, right? The sphere is kind of like our planet. It looks like this. Only the surface of the sphere, right? The equation of the sphere with center, say x1, y1, z1, with radius r. The equation for this geometric object is x minus x1 squared plus y minus y1 squared plus z minus z1 squared equals r squared. Okay, that's the equation of a surface with center x1, y1, z1, and with radius r. So if we want to see how we can use, for example, this website I showed you. So here, for example, if you look at the left side, you see it's written z equal, right? It means you should write the equation in terms of z. If you want this page to kind of graph the equation for you, let's do that. Let's look at our equation. Let's go back again. So let's suppose, for simplicity, let's suppose we are looking at a sphere with center which its center is at the origin. So the center is 0, 0, 0. and say the radius is 1. Okay, so the equation would be x squared plus y squared plus z squared equals 1, right? That would be the equation of a sphere around the origin with radius 1, okay? Now, sometimes we like, or we can write everything in terms of one variable equals the rest. So for example, here we can write it as z squared equals to 1 minus x squared minus y squared, right? I can take x squared and y squared to the other side. That would be what I would get. That's what I get. And then I can take the square root of both sides. Z would be equal to square root of 1 minus x squared minus y squared. Okay, is that correct? Is it correct? If I take the square root of both sides, would I get z equal to square root of 1 minus x squared minus y squared? Or there's something I'm missing? Any comments? Yes, plus or minus. Thank you. So it would be plus or minus this thing. Okay, now let's go back to look at this. Let's go here. It says z equal to. So here we have z. What we got was z is equal to well, square root of, yeah, okay. So at least let's look at one, let's look at half of the sphere, semi-sphere. 1 minus x squared minus y squared, square root of that. Rather than writing square root of that, I can write with power 1 over 2. Right? I can write with power 1 over 2. And the graph would be what you see here, the semisphere. So let's see if we can add plus minus. Does it understand now? Okay, I'm not 100% sure how I should tell it as plus or minus, but we see here the plus part. I think this QRT would still give the same thing. We can try. No, it doesn't understand QRT. Okay, anyway, we have the half of the sphere here. If we write the minus sign here, we get the other half. Okay. Let's, is there a problem with the voice? Okay. Let's, so let's look at, okay, let's look at the other surfaces. So the first thing we saw was a sphere. The second interesting thing is, well, a cylinder. Okay, so inside our three-dimensional space, this is a three-dimensional space, right? This is X, this is Y, this is Z. We have our three-dimensional space. Now, here, there are three important planes. This is one of them, the blue one, which continues in the other directions too. This is a plane, right? The other interesting plane is this one, the yellow one. It's a plane there. And then the other important plane is this one. Right. There are 3 planes. We call them using, well, the axis which this plane has. We call this one the XY plane. We call this one the XZ plane. And we call this one the YZ plane. Okay. There are 3 planes we have here. Actually, we can write down its equation. What is the equation of, for example, XY plane? Let's just look at the XY plane. Here we have, this is the plane we are talking about, X, Y, Z. What is property of every point on this plane? Let's take a point P on this plane. Well, if we take different points here on this plane, we can look at their components. They have some X, they have some Y, they have some Z. Well, their X, the first coordinate they have, it can be different. This point has some X, say X1. This point has another X, X2. They can have different Y. This point here has Y1, this point has Y2, this point has Y3. It seems X and Y can be anything. What about Z, the third coordinate, the height of these things? Well, it seems the height of all of them is 0, right? Z for all of them is 0. So the third coordinate is actually 0. What does it mean? It means Z is equal to 0. Z equals 0 is this XY plane. Z equals 0 is the XY plane. Z equals 0 is exactly where this XY plane is. We have other planes too, and we can describe them in a similar way. For example, if you look at this blue plane here, which contains the x-axis and the z-axis, if we choose different points here, we can see these points have different x variables. They have different z components. But they all have something in common. What is the, say, let's show these points with x and p and q. What is the second variable of these points? What is the second component, the y component? Well, for both of them, y is 0. They are here. See, y here is 0, here is 1, here's 2. For these points, y is always 0. So these points are of the form x, 0, z. So y is always 0 there. So y equals 0 is the same as xz plane. We can try that here too. So here, if I let z to be equal to 0, I would get this xy plane. You see, maybe this is the better angle. Here we have x. I think you see my mouse pointer. Here we have y. Here we have z. If z is equal to 0, we have this plane. But what do we get if z is equal to 1? We get the plane above it. What if z is equal to 2? The plane above it. So this is the z equal to -1. 0. What about -1? -1 is here. What about -2? -2 would be, well, it would be down there, but because it's out of our range, it doesn't show. We can. Now, let's see if we can change. Okay, it should be in terms of z. There was a double minus. Oh yeah, you're right. I thought it's, yeah, that would be -1. Thank you. Okay. So we have the planes in our three-dimensional space. Now, look at these planes. In each plane, for example, here in XY plane, we can look at the circle in S1, SY plane. Maybe it looks more like an ellipsoid. Let's circle there. Remember, when we are in a plane, say XY, we can have a circle, say, with center x1 and y1 and radius r. Okay, in two-dimensional space, the equation for this circle was x minus x1 plus y minus y1 squared, x minus x1 squared plus y minus y1 squared equals r squared. That was the equation of a circle in a plane. Now in three-dimensional space contains a two-dimensional space inside it, and that's this xy plane we have here. We can think about this two-dimensional space on the right side as the plane inside three-dimensional space. So three-dimensional space contains this two-dimensional space, which is this one. I can just put it there, that two-dimensional space, and then there is the axis. So this circle here would be here, right? This blue circle I have in two-dimensional space. If I put all this two-dimensional space, if I put this two-dimensional space inside this three-dimensional space, that blue circle would be there, right? Now, what is the center of this circle? The point is that the center of this circle, well, if the center of the circle on the right-hand side is, maybe it's better to draw a more, well, we can continue with this one. If the center on the right-hand side is 0 and 0, the center of this circle there is also 0 and 0 and 0. Now it's three-dimensional space. We need three components. The last component is the z component, but the z component is also 0. Now look at the cylinder which passes through this circle, this cylinder. I want to write down the equation of this cylinder. What is the equation of this cylinder which passes through that circle and is parallel to z? So there are two important things about this cylinder. One, it contains the circle in xy plane, and two, it is parallel to the z-axis. There are two things which are important, okay? The first thing, this circle, so maybe I draw it again. There is this circle. And the second thing is a direction. You're looking at that direction, z direction. This circle is called the generating curve. Generating curve. We can choose another curve and we get another surface. So for example, if rather than a circle, if I had, say, this curve in xy plane, this is xy plane, for example. Here I could get another plane in xy plane. Now here my generating curve is not a circle, it's another curve, right? And then I have a direction. I have a direct, right? A direction. If I move this curve in that direction, again, I would get a surface. That's how this surface is going to look like. Right? Does it make sense? I can take another generating curve. My generating curve might be something else. It might be like this. This time, if I move it in another direction, in this direction, the surface I would get would look like this. So for any curve and any direction, I can move that curve in that direction and I would end up with a surface. All these surfaces, even if they are not literally a cylinder, all these surfaces, this is another example of these things, they're called cylindrical surfaces. So cylindrical surfaces, they come with two important pieces of information. One is the generating curve. Here, the generating curve is this blue thing. And the other is the direction we move that generating curve. Okay. Now, let's go back to look at our cylinder here. In this cylinder, the generating curve is x squared plus y squared equals 1. The circle in xy plane. That's our generating curve. The direction is the z direction. We are moving the generating curve in direction of z. The question is that what is the equation of this cylinder? Okay. One thing we should understand here is that when we are moving this cylinder in direction of z everywhere, for any z, we have the same circle. So for example, when z is equal to, when we have such a cylinder in xyz plane, when z is 0, we see this circle, x squared plus y squared equals 1. When z is 1, what is the equation of the circle we see? What is this circle? What is the equation of this circle? Do we see the same circle or it's another different circle? If you just think about it as a circle in plane, think about this circle as a circle in a plane. It's completely the same circle. So it should have the same equation. What about the case where z is minus 1? Well, we see again the same circle. What does it tell you? It tells you this equation is independent of z. It doesn't have anything to do with z. For any z, the equation is x squared plus y squared equals 1. You see, z has nothing to do here. The equation is always x squared plus y squared equals 1. Let's look at another case. That was the equation of the cylinder 2. So if you write x squared plus y squared equals 1, so this equation, x squared plus y squared equals 1, if I ask you to graph the geometric object which this equation represents, you should ask me in 2-dimensional space or 3-dimensional space. In 2-dimensional space, it would be this circle. In 3-dimensional space, it would be this cylinder. And it makes sense because if you look at this 2-dimensional space inside 3-dimensional space, the only thing you would see is the intersection of that circle with 2-dimensional space. If you are a being which lives inside that 2-dimensional space, you would only see this intersection, which is exactly the circle you have here, right? No, there is no caps. You're right. This this really goes to infinity in both directions. That is true. It's not bounded in any way. It's just like a line. Okay, we can do the same thing in other directions. For example, suppose we can look at this XZ plane. Okay, there is a plane here, right? XZ plane. This is this XZ plane. This is this plane. Let me show this plane with red axis. What we have on the right side is the plane which we have in three-dimensional space. I'm just drawing it on the right side too, okay? Here on the right side, let's look at this plane. And then let's look at the circle centered at 0 with radius 1, okay? What is the equation of the circle in XZ plane? Well, it should be x minus 0 squared plus the second coordinate used to be y minus 0 squared, and everything should be equal to 1 squared, which is 1. But here we don't have y. The other coordinates, the other direction, instead of y is z. So instead of writing y in the equation, we should also have z. So it's x squared plus z squared equals 1. Now this circle, we can see it in the three-dimensional space too, right? And we can move it parallel to y direction. What we would get is a cylinder like this. Now, if you want to know what is the equation of this cylinder we have here, which is parallel to the y direction, we can do the same argument. We can see if y is equal to 0, we have this circle here, which is x squared plus z squared equals 1. If y is 1, we see the same circle, x squared plus z squared equals 1. If y is anything else, we still have the same circle. So the equation of this cylinder, independent of y, is x squared plus z squared equals 1. That's the equation of this circle. So this cylinder. So if we have this cylinder here, the equation is x squared plus z squared equals 1. I can talk about that circle in two-dimensional space. The equation inside three-dimensional space is a little tricky. I wouldn't talk about that now. At some point, I would mention. It's something we will get back to. It's a good question. Thank you for asking. But it needs a little bit background. So the equation of the cylinder is this. X squared plus z squared equals 1. So z squared is 1 minus x squared. Therefore, z is square root of 1 minus x squared. But again, remember, we always have plus and minus. Okay, we can use this equation now to graph it also here. So the equation is plus or minus. Let's look at plus first. x1 minus x squared. The whole thing was the square root of that, which is the same as power 1 over 2. So this should give us half of the cylinder. And as you can see, it does. This is half of the cylinder. And if I write minus square root of 1 minus x squared, I would get the other half, which is here. We can look at the other half of this cylinder. So that's how we can, well, write down the equation of cylinder. Okay. Okay, now let's consider other cylindrical surfaces. We can have, so in order to have a cylindrical surfaces, we should have a curve, whatever it is, and then we should have a direction, and then we can start to move that curve in that direction, and it would give us a surface. It doesn't need to necessarily be a circle. It can be anything. We can, it's just like literally moving that curve in that direction. Now, I want you to sketch the surface, which is represented, its generating curve is z equals y squared, and the direction you're supposed to move it is the x direction. Okay, sketch it, and then I would allow you to share it. Let's see if you can sketch this one or not. So spend a few minutes to sketch this one, and then you would be able to share it with others. Raise your hand if you have the sketch. Oh, that's good. Do you want to share it with others?
How exactly would I do that?
Okay.
Like,
wait. Okay, now you can see, if you want, you can, if you want, you can share your screen, or you can share one specific thing, I guess. I allowed you to share. You can, if you have something to share, you can do it now. Or I guess you can like take a screenshot and send it to me. I think that would also work.
okay, all right.
For
Okay.
Mariam, also the same thing. If you want, you can, I think, take a screenshot and send it to me. I think you can send a file right here, actually, I guess, through Zoom. Or you can email it to me. That would also work, whatever works for you. I want to see what are your drawings. Yeah, that's a good idea. If anyone can sketch the graph, you can take a screenshot and email it to me, and we can see it right now here. Okay, we have one, I received a few things. Let's see. Okay, that's one we have here. That's good. It's, well, let's see. We have YZ plane here, and we have parabola, and we moved it in direction of X. That's correct. Let's see if we have any other, did I get anything else? No, yeah, that's it. Yep, that's quite good. That's correct. We can, that was correct. We can try it here to see. It's okay. It's fine. We can look at the equation here too. How should I write down the equation? If I want to write down the equation, it should be equation for z, right? So let's go back. Okay. Okay. So how can I write down the equation for z? Can anyone tell me? Because I need to say what is z in 3D space, right? So here is x, y, z. In plane, we have in YZ plane, we had an equation, right? How can I write down that equation for something inside all three-dimensional space? What would be the equation in 3D? Well, yes, z equals y squared here, but same argument, because it doesn't matter which x we use, we see exactly the same thing. It means this is really the equation everywhere in three-dimensional space. So z should be equal to y squared. Let's try to see if we are right. If z is really equal to y squared, what is the correct direction of it? Okay, that's interesting. Z equals to y squared. Okay, that's it. Yeah. So here we can see this parabola moved along the x-axis. Z equals y squared moved along the x-axis. Okay. Okay, let's continue with oh, we had another example too, I guess. We had z equals, well, sorry. We had y equals sine of x. If you remember from Calc 1 or Calc 2, the graph is like this, right? And it continues. Inside three-dimensional space, we have x, y, z. This graph here would look like something like this. And if we move it in z direction, what we are going to get is something like this. And the equation in the plane still is independent of z, so still the equation is this. We can do this in another direction too. So for example, if we look at x, y, z, if we look at x, z plane, if we had z equals sine of x, it would have been something like this. And we could move it in y direction. It would have become something like this. Right? That's what we would get. And the equation again is independent of y, so the equation still would be z equals sine of x. Again, we can try to visualize that here too. Z equals sine of x. Well, minus 22 is not enough. Oh, it's too much. Maybe minus 5 to 5 makes more sense. Yeah, this is our sine function moved in one direction, right? We could take cosine, we could take tangent. You see, it's like our tangent graph, if you remember how does the tangent graph look like, it's like we moved it in one direction. Or if you remember the ln, it's like we moved ln in one direction. Or anything, basically. We could have a line and move it in one direction. If we move a line in one direction, if we have a line and move it in one direction, we would get a plane, right? We could do it with anything else. We could do it with x cubed. That's if you look at the graph of x cubed in plane, it would be something like this. And if you move it, you would get this surface. Oh yeah, you should definitely remember, review trigonometric function. Very soon when we get to derivative and integral, we should use a lot of that. I would do a review, but you should also review that, right? I am going to review that, but you should review it too. Actually, trigonometric functions are important, right? Okay, anyway, so the second part is even more interesting. We are going to get to so-called quadric surfaces. Okay, these surfaces are well, any equation, a general equation of surfaces we saw here, they contain x, y, and z. This which they have things like x squared, like this. They have y squared. They have z squared, like this. The degree is 2, at most is 2. For example, they have x, y. The degree of this term is also 2. We have the degree of x is 1, degree of y is 1, degree of x, y is 2. They have, for example, x, z term. They have y, z term. And they might have x, y, something in terms of z, a constant. This is the kind of general form of a quadric equation in plane. We like to see what is the geometric object this thing presents. So first thing, note that equation of a sphere with center 0, 0, 0, radius 1 would be something like this: x squared plus y squared plus z squared equals 1. I can bring 1 to the other side. Minus 1 equals 0. So what we have here, we are kind of, is a special case of the thing I'm telling you now. I'm telling here x squared, y squared, z squared all have coefficient 1. What if we start to vary these coefficients? What are the geometric things we would see? And actually, we can get a lot of interesting things. So x squared plus y squared plus z squared equals 1, right? What about x squared over 4 plus y squared plus z squared equals 1? This thing gives us a sphere. This thing gives us sphere. What does this thing give us? What is the geometric object we would get from the other one? Can anyone guess? It is analogous to ellipse. In three-dimensional space, we call it ellipsoid. Okay. How does it look like? The point is that if we have three directions, x, y, z, when we are dividing x squared by 4 by big number here, it's like y squared is like divided by 1, z squared is like divided by 1, right? It means x squared divided by 4, it means look at the root of this number, it's 2. 1, 2. Find that number on x-axis. The root of this number is 1, the square root. The square root of this number is also 1. It means our ellipsoid would pass through these points. So it's kind of more extended in x direction, more than a sphere. It's more like an egg in x direction. So when we divide x squared by a number, that's what we are going to get. So x squared over 4 plus y squared plus z squared would be equal 1, would give us something like this. Okay, so z squared would be 1 minus x squared over 4 minus y squared. Z, if we take the square root of both sides, z would be plus or minus square root of 1 minus x squared over 4 minus y squared. We can look at the graph of this function too. Let's look at the graph of this function to see exactly how it looks. So there are two parts. One is plus, one is minus. First, look at the plus part. 1 minus x squared over 4 minus y squared. Okay, let's get closer. Let's rotate. Yeah, this is, so it's going to be like this. You see, it kind of look, it's the, well, it is the northern hemi-ellipsoid. This is the other part. We should glue these two things to get the complete picture. I'm not sure how to look at both of them at this. Oh, I think I understood. What can I do? Did I? Okay, I'm not sure. So there is this plus part and there is minus part. You can see it's kind of looks like sphere, but yeah, I look, there is no plus minus anywhere. It seems they are not considering the case where there are kind of, there are two equations for the thing. No, I tried that. It doesn't allow me to add another function. It should actually. Yeah, you're right. Thank you. I should add another function. And then I should make it minus. And then ask to show that one too. And for some reason, okay. There is a glitch here. What is this thing? It has a tail. It's correct, but there is just a tail here. Okay, then. That seems cool. Okay, yeah, this is the whole thing then. Yeah, that's excellent. Good, very good. So here we can see, this is x squared, it's x squared which is divided by 4, and you can see it's extended in x squared direction, right? Number of grids are different. Really? Oh, yeah, that is also something which is correct. This is 30 for this one. Oh, no, it's the same. It's the bounds are different. Maybe if we choose the same bounds for both of them, it would work better. Number of grid lines 30, number of grid lines 30. No, it doesn't really matter. I mean, I like its tail. If you draw a tail in the exam, it would be fine. I wouldn't reduce any point. So here, and the number of grid lines are also the same here. So, so if we divide, for example, x squared by, say, 3, the amount which we kind of, the amount which we push it in x direction would become a little less, right? If we divide it by 2, you can see it's getting closer and closer to sphere. If we divide everything by 1, we would get a sphere. Now, if I divide y squared by a number, what would happen is that in direction of y squared, we would have and kind of pushed in y squared direction. You can see that now. Okay, so anyway, that's how it works. That's how it works for these ellipsoids, and they're pretty interesting things. Okay, so the first thing we talked about was ellipsoid. So in most general case, an ellipsoid is something of the form x squared over a number, say a squared plus y squared over another number, b squared plus z squared over another number, c squared equals 1. And they look like this inside three-dimensional space. The important thing is that all of these signs here are positive, plus, plus, plus. None of them is minus. That's the important thing. So a natural question would be, what would happen if we change one of these signs? What would we get if we look at x squared over a squared plus y squared over b squared minus z squared over c squared equals 1? Let's say, what is x squared plus y squared minus z squared equals 1? What is the geometric object this equation represents in three-dimensional space? Any idea? It's similar to hyperbola. It's called, just like we call it the other one ellipsoid, we call this one hyperbolic. Yes, that is true. So let's see how we can argue to find this geometric object. There's a way to guess at least how they look like. The idea is that in three-dimensional space, x, y, z, there are a lot of planes, right? Just like a line is on a line, there are a lot of points. There are infinitely many points on a line. In three-dimensional space, there are a lot of planes you can imagine in your mind, right? You can look at these different planes. So for example, y equals 0 is a plane. I told you y equals 0 is the xz plane. Maybe it's good if I show it one more time to make sure we understand this thing. So let's look at z, for example. Z equals 0 is this plane, right? Z equals 1 is this plane. Z equals 2 is this plane. Z equals 1/2 is this plane. Z equals 1/3 is this plane. Z equals 1/4 is this plane. Z equals -1 is this plane. There are a lot of planes which they go in one direction. We can have planes in other direction too. We can have y equals 0, y equals 1/2, things like that, right? So for example, here, y equals 0, this is y. This is where y is 0. Y equals 0 would be this plane. This is where y is equal to 0. y equals to 1, if this is 1, y equals to 1 would be this plane, the blue plane, right? Y equals -1 would be the green one, right? There are a lot of planes next to each other. Now, if you look at this equation, x squared plus y squared minus z squared equals 1, if you want to sketch this one, I might ask you in the exam to sketch the graph of this equation, the graph of the algebraic object, which the geometric object which this equation describes. That's what you should do. You should say, if y is 0, what would I get? I would get x squared minus z squared equals 1. What is x squared minus z squared equals 1? It means x squared minus z squared equals 1. It means z squared is 1 minus x squared. Does anyone know what is the graph of this function? Has anyone seen this before? It is hyperbola. So, okay. Let's talk about that. We need a little background then to talk about this. Let's talk about slightly simpler case. X squared minus y squared equals 1 in xy plane. I want to graph this function. Let's go into two-dimensional case, which is slightly easier. I want to find the graph of this equation inside two-dimensional space, okay? How can I do that? Well, x squared minus y squared equals 1. What does it tell me? How can I find a point? Let's find a few points first. It might give you an idea. One point which is on this graph is 1 and 0, because 1 squared minus 0 squared is equal to 1. So 1 and 0. Here is a point on the graph of this function. -1 and 0 is another point on the graph of this function, because -1 squared minus 0 squared is equal to 1 minus 0, which is 1. So this is another point on the graph of this function, okay? So, okay, can we find any other point here? For example, if x is 2, what would be the value of y? It would be actually square root of 3. Yes, that is correct. So 2 squared minus the square root of 3 squared would be 4 minus 3, which is 1. 2 and square root of 3 is somewhere around here. This is 2 root of 3, it's somewhere around here. And we can try different points. If we try to connect them, we would see we get something more or less like this. Right? This is called hyperbola equation, or hyperbolic equation, actually. So let's go back now. Here we have x squared minus z squared equals 1. We have one of these things we just saw, but in xz plane. It should be something like this. This is x, this is z. The red one is the xz plane. We should have like something like this in xz plane. And what if y is equal to 1? If y is equal to 1, we have x squared plus 1 minus z squared equals 1. X squared minus z squared plus 1 equals 1. We can cancel 1 with 1. It means x squared minus z squared equals 0, x squared equals z squared. Therefore, x is equal to plus minus z. So x equals to z, if we look at x, z plane, x equals z is this line. X equals to minus z is the other line. We should draw these two lines here. And if we look at the green one, this one, what are we going to get? We are going to get x squared plus 1 minus z squared equals 1. Again, these two would cancel. X squared would be equal to z squared. If you take the square root, we get x equals plus minus z. So in the green line, we get also, in green plane, we also get these two lines. We kind of try to guess what is going on, what's happening, by kind of combining these things in our mind. It's a little, it might be a little hard if you haven't seen these things before. Okay, I would show you what will happen. Okay, let's look at this plane. Okay, z equals to what? Okay, maybe it's better first if I derive the equation in terms of z. So x squared plus y squared minus z squared equals 1. This is the function we want to find, right? It means z squared is equal to x squared plus y squared minus 1. So z is equal to plus minus square root of x squared plus y squared minus 1. Let's sketch the graph of this one. Well, let's ask computer to sketch the graph of this one. Okay, we should add another one. And okay, we have two of them. One of them is plus, the other one is minus. 1/2 x squared plus y squared minus 1. Same thing with minus. That's how it's going to look like. It's kind of hard to guess if you haven't this thing before. Maybe this is very confusing. Maybe if I draw the graph first for you, it makes more sense. X squared plus y squared minus z squared equals 1. This is x, y, z. The thing we are going to see basically is something like this. In direction of z. It's in direction of the one which has negative sign. You see, it's in direction of z. If we had something like x squared minus y squared plus z squared minus 1. So this one was negative. What we would have in x, y, z plane, it would have been something like this. And if we had minus x squared plus y squared plus z squared equals 1, we would have something like this. So it would kind of extend to infinity like this. That's what we would see. Yeah, I can go back for a second. Yeah, I mean about, well, not torus, about these. Yeah. We considered here the case where all of them, all the terms are positive. We considered the case where one term is negative. There is another case where two terms are negative and one term is positive, right? So what if we have, say, x squared minus y squared minus z squared equals 1? So we have only one positive and two negatives. Two negatives. How is it going to look like? So again, it's kind of hard to imagine if you have not seen this before. So the idea is kind of the same. We should try to kind of sketch it for different values. We should try to give different values to one of these coordinates. I would just choose z. It really doesn't matter. You can choose x or y. I ask myself, I would tell myself, look at z equals 0. Z equals 0 is this plane here, right? If z is 0, x squared minus y squared minus z squared equals 1. So x squared minus y squared equals 1, right? Well, okay, maybe I would, let me think a little. For educational reasons, maybe it's better to consider the case where, especially because of the application we are using, it's better to consider the case where x and y are negative and z is positive. There is no difference really, but let's just take this one. Okay, what would happen if z, so what matters is that what would happen if two of them are negative and one of them is positive. Okay, if z is 0, we would get minus x squared minus y squared equals 1, which means x squared plus y squared equals minus 1. Well, x squared plus y squared can't be a negative number. There is no answer. So if z is 0, there is no answer. What about the case where z is 1? Well, then minus x squared minus y squared plus 1 equals 1. I can cancel these two numbers. In other words, x squared plus y squared equals 0. X squared plus y squared equals 0. Okay, z is 1. It's here. Z equals 1 is the plane here. What is this equation? X squared plus y squared equals 0. It's an equation of a circle with radius 0. What is a circle with radius 0? That is correct. A circle with radius 0 is a point, right? If you think about a circle, which its radius is 0, it's just a point. So here we have a point. What about the case where z is 2? We would get minus x squared minus y squared plus 4 equals 1. So x squared plus y squared equals 3. This is equation of a circle with radius square root of 3. So here when z is 2, we get a circle. We can continue that. We would see we would get bigger and bigger circles. We can connect them. We would end up with something like this. And we could do it for negative z. We would end up with something like this. So maybe I should go back and add it to our list. The last thing, which is called hyperboloid of two sheets. So it has the same name as this one, but this is called one sheet hyperboloid. This is called hyperboloid with two sheets. It's something like minus x squared minus y squared plus z squared equals 1. And maybe I would write it here. Minus x squared minus y squared plus z squared equals 1. And it would look like this. Let's go and try it here. Okay. So, oh, maybe I should write down the equation first. So minus x squared minus y squared plus z squared equals 1. So z squared is 1 plus x squared plus y squared. So z would be plus or minus square root of 1 plus x squared plus y squared, right? So that's the equation for z. So z would be plus or minus 1 plus x squared plus y squared. And that's what we would get. Okay, I hope it makes sense, huh? I would write it down again. So this is the last thing. So let's summarize. Let's summarize one more time. If you have an equation like x squared plus y squared equals 1, which doesn't have z in it, it means it's a cylinder. So it's something only in terms of two variables, no z. It means it's a cylinder. So it's a cylindrical equation. And it's something in the direction of the variable which do not appear, which is not here, which doesn't appear here. The other thing we had was a sphere, x squared plus y squared plus z squared equals 1. It was a sphere with radius 1. The other thing, so it's just a sphere. The other thing we had was ellipsoid. Something of the form x squared over 4 plus y squared plus z squared equals 1. It's like an egg, and it's extended in the direction which has larger denominator. Then we got to things which are of the form x squared plus y squared minus z squared equals 1. There is one negative term, right? This is hyperboloid 1 sheeted. It's like this. It's extended in the direction with negative sign. So if z is negative, it would be extended in direction of z. What if we have two negative ones and one positive one? It would be something like this. Now, this time, it would be in the direction of the positive one. It's extended in direction of the positive one. Okay, is there anything I'm missing? From this list? So the last one is hyperboloid of 2 sheets. Okay, so there are two more, but before getting to that, we can have 15 minutes break. So there are two more of these I should tell you about. Let's come back at 10:45. Two more types of surfaces, actually, which we should study. There are two ones which we have not studied yet. One of them is, we consider the case where x squared plus y squared minus z squared is equal to 1. And I said it would look like, it would be something like this. What if it's, and for any non-zero number, like 1, 2, any positive non-zero number. Here you have a positive well, when I say positive, it means it's non-zero, a positive number. But what if it is 0? X squared plus y squared minus z squared equals 0. The point is that when we are, for example, what's the difference? In order to answer that question, we can answer another question. What's the difference between x squared plus y squared minus z squared equals 1 and x squared plus y squared minus z squared equals 2? The answer is that this thing becomes more, well, I can actually show you the difference. It might be interesting to see how these two things are different. So maybe before going to a new equation, let's just look at these two equations and see what's the difference between them, right? Here, in the first case, z squared is equal to x squared plus y squared minus 1. So if you take the square root, z would be plus or minus square root of x squared plus y squared minus 1. In the second case, z squared is equal to x squared plus y squared minus 2, which means z is plus or minus square root of x squared plus y squared minus 2. Right. Now let's look at our the graph of these two functions, right? So once we have what x squared plus y squared minus 1, this is going to be the first thing. It looks like this. Now the question is, what would happen if rather than minus 1, I choose minus 2? Okay, it has changed. What's the difference? Bigger radius, yeah, that is true. Bigger radius. So when we do it, when we have minus 1, the radius is smaller. That is correct. For example, what if you have, rather than minus 1, we have minus 1 over 2? The radius would get even smaller. It becomes like this. Here it becomes thinner. It loses weight. It's like it lost some weight. And when you raise it, it got fatter. That is correct. Yeah, you're right. What about if it's 1 over 3 rather than 1 over 2? Well, it becomes like this. What about 1 over 4? It will become thinner too. 1 over 5. Thinner. 1 over 20. Well, we are getting to 0, right? 1 over 20 is even smaller. What about 1 over 200? They are still connected, you see? But if you zoom in a little bit, you can see what's going on. What about 1 over 2000? What about 0? Yeah, you're right. What if we, rather than 1 over 2000, what if we have 0? This is what we are going to get. So if I want to draw the idea a little more schematically here. So when we have x squared plus y squared minus z squared equals 1, we get something like this. When we have x squared plus y squared minus z squared equals 1 over 2, we get, well, let me show this one with red. We get something like this. When we have x squared plus y squared minus z squared equals 1 over 100, I would show the blue ones, we would get something like this. When we get to 0, x squared plus y squared minus z squared equals 0, these two curved lines, they get so close to each other that they would have intersection. You would get this thing. And then if we go one step further, if we go, so they are like this, then we have positive. When we have 0, it becomes like this. When we have negative, they are, first these two curves, they get to each other, becomes like this. The next step is that they even become disconnected. So it would be negative. So you can think about it as a kind of a continuous thing. When it's plus, it's like this. Slowly, they become closer and closer. At 0, they are like this. And then when you continue, they become like this. And then they, as we are like making this thing bigger and bigger, they even become more and more fatter and fatter. Okay. So we can think about these surfaces as all of them are kind of similar. This new thing is called elliptic cone. This is quite important. This one, x squared plus y squared minus z squared equals 0 is in direction of z. It's in direction of z. It's called elliptic cone. Why is it called elliptic? Because if you look at these like sections of this thing, you would see an elliptic curve, an ellipse. Okay, so if we had something else, if you had, for example, if the -1 was in, if the coefficient of y squared was negative, we would have same thing, but in direction of y, right? And if x was negative, x squared was negative, we had the same thing in direction of x. Okay. Now, there's one more thing, and that's the case where we have x squared plus y squared, but rather than minus z squared, we have minus z, right? So we had z squared. Now, what would happen if we have x squared plus y squared minus z equals 0? Well, here the answer was this thing. What do we get if we have x squared plus y squared equals z? So this means z is equal to x squared plus y squared, right? Well, if we had you're kind of correct, yeah, one side is correct. So if we had, there is one first thing to note, and that's x squared plus y squared, this thing can't be negative. Can't be negative, right? The squared of numbers are positive, their sum would be positive. So this thing is equal to 0, so z should be greater or equal than 0. So the first thing is that there is nothing down there. You know, it's only above this floor. And the other thing is that, remember, if we had x and z, if we had z equals x squared, it would be something like this, right? Z equals x squared would be something like this. So even if here, if you look at the case where y is 0, we get z equals x squared, that would be something like this. If we look at the case where x is 0, z would be equal to y squared, which is something like this. If we kind of, maybe it's better to go to a new page. So z is equal to x squared plus y squared. I'm saying it's very similar to two-dimensional case where we have only z and x. If z was equal to x squared, we would have something like this. So three-dimensional version of this thing is, it's quite similar. It's z, x, y. It's something like this. It's very similar to this thing. It's just, it's three-dimensional version. Let's make sure. So so z is equal to x squared plus y squared. There is no other equation. There is, okay, that's what would we get. Let's maybe change the scale. Okay, so that would be the answer. And that's the last one, actually, which we care about here. So, so let's summarize everything for one last time. So we started with equations like this: x squared plus y squared equals 1, which there is no z. Yeah, I would mention the name. So no z. These are cylindrical equations, which they are like this. The other thing we saw was something like x squared plus y squared plus z squared equals 1. This is sphere. Looks like this. The other case was x squared over 4 plus y squared plus z squared equals 1. This is ellipsoid. It's extended a little bit in direction of the variable which has larger denominator. The other thing we looked at was x squared minus x squared. Well, one of them was negative, say z. X squared plus y squared minus z squared equals 1. It was hyperboloid. One-sheeted. Next case was the case where we have x squared plus y squared minus z squared equals 0. We get something like this. This is called elliptic cone. The next case is that when the number we have on one side is negative, or we can say two of these numbers by multiplying by -1, we can say two of these things are negative and the other one is positive. This is something like this. This is two-sheeted hyperboloid. And then we have what we just saw, x squared plus y squared minus z equals 0. It would be something like this. We have just one of these, one of these sheets here, and it's called, well, it's called elliptic. I mean, the names don't matter much, but it's good to know them. Parabola. Okay. There's one last thing. Well, if you want to take a screenshot or something from this page, you can do that. Now let me add just one more interesting thing, and that's the case where z is negative. So as we have c here, x squared plus y squared minus c, but this sign is also negative. So a new thing would be, for example, x squared minus y squared minus z equals 0. So let's consider that case too. X squared minus y squared minus z equals 0. I don't expect you to be able to draw that. Maybe it's better to say x squared. Maybe it would look better if I make this plus. Maybe, so let me just tell you the name. The name is hyperbolic paraboid. It's kind of look like kind of saddle. You know what is saddle? The saddle of horse, for example. It looks like this. Kind of looks like a saddle. Actually, it should go through 0, maybe. Saddle is not very good saddle. So it's also called a saddle. And it's kind of extended in direction of y, the one with the negative sign. So here z is equal to y squared minus x squared. Let's sketch this one. Let's see this one too. Okay, so this is what we would get. This is like saddle of a horse or something like that. Yeah. Okay, so these are the things we have. These are the quadric surfaces. So we had, so we just defined quadric surfaces. We had cylindrical. We have sphere. A more general sphere is ellipsoid. We have hyperboloid. There was one sheeted hyperboloid. There is, well, of course, hyperboloid of two sheets. There was elliptic cone. There was elliptic paraboloid. And the last one, hyperbolic paraboloid. You don't need to memorize the names, of course, but it's good to have an example of each of them in mind. I think there is a table in the book which has all of them, has the sketch of these things. Okay, that's for that. There are two, well, maybe one or two. Let me see. Yeah, there is one more type of surface which I wouldn't talk about it today. It might confuse you a little more. It's called, the last kind of surface we have in the book is surface of revolution. I would talk about this one on Tuesday. I would post one speaking about this one. Because it is a little computational and we should dive into computing a lot of examples and stuff like that. But beside surface of revolution, we're done with these surfaces. Okay, is there any question about these surfaces? One homework you would have for the next week is to look around you, like in your house or like in the nature or like around you, or if you don't go outside, you can just Google and search. And I want you to find these example of these surfaces in real world. So for example, it's very easy to find a cylindrical surface. Probably you can find that in your home, right? It's not hard to find a cylindrical surface. Or it's easier to find a sphere, right? Probably you would find a sphere in your home. But what about the others? I want you to look at the other surfaces you would see around yourself. And I want you to kind of recognize them, you know. If you can't find it, you can Google and see if you find them in nature. Like if there is a specific plant which looks like one of these things, or if you can find them in the ocean, wherever. I want you to search and find example for these surfaces in nature, for each of them. And try to find good examples. There are some very, very, very interesting examples. I wouldn't spoil it for you, but you can search and you can find them. Also, you might, as I said, find some examples around yourself. Okay.
Here's a good puzzle. It comes out of an old Sherlock Holmes story. Looking at the tracks from a bicycle, can you tell which way the bicycle went? Why not pause this video and figure it out?
Okay, let me repeat the question because I was not recording apparently. So we have a trace of a bicycle on the ground, trace of a bicycle on the ground. And the question is, if we just look at the trace, can we guess if the bicycle was going right or it was going left? Right, just by looking at this trace, can we say which direction the bicycle was going, right or left? That's the question. Think about it for 2 minutes. I want everyone to think about it because it's really related to a concept in our course. So let's think about it. Okay, depends on the starting point, maybe where the track starts. Well, suppose we only have part of the track, right? Suppose for some reason we don't have that part of the track and that part of the track anymore. We don't see that part, right? Suppose for any reason we just have a part of the track is visible to us. Okay, can we understand based on we don't have the starting point of the track, we have only part of the track. Suppose there is a photo taken of that part and you're seeing the photo. Based on that, can we deduce if the bicycle was going right or left? No, well, there's a good question. If you look at bicycle's track, would it look like a line or you would see two lines? Well, if the bicycle is going in a completely direct way, so if the bicycle is, if you're riding the bicycle like this in completely direct, straight direction, right, you would see a line. But if you are not going, if you are going around and you are not riding in completely direct direction, you are not going to see a line anymore. You are going to see two different lines, like curves. Each of them belongs to one of the tires. Yeah, well, but here that is true. If you have a bicycle, this tire would have its own line and this one would have its own line. Well, my graph is not very good actually, because in my graph both of them are on one line, so probably I should draw a better one. So each of these tires would give us one of these things. So say one of them is on here. One of them is on this one, and the other tire is on this one, and that would make more sense, right? Something like this. Okay, we have some solutions here. Well, they are in some sense correct. So one person has mentioned both tires start turning at the same time. So the back tire makes smaller circle. That's kind of correct, but can you explain? Can you elaborate on that? Can you explain why that would be the case? So, well, this is the back tire in our case. So when we turn left, for example, first this one would turn left, right? And then the back tire. Or would they turn at the same time? That's kind of correct. Let's watch the video. Let's continue watching the video. Maybe it would becomes a little more clear.
Okay, we're back. Before I tell you the answer, let's ask a more basic question. Which track is from the front wheel and which is from the back wheel? And I think some of you didn't actually pause the video for my first question, so I'm going to give you another chance. I want you to pause now, look at the tracks, and answer two questions. Which track came from which wheel, and did the bike go to the left or right? Okay, have an answer? I like this puzzle because it leads you to ponder some notions from a branch of mathematics called the differential geometry of curves, which originated with the beginning of calculus in the 1600s. The key observation is that the two tracks are not independent, like say two unicycles would be. The front and rear wheels of the bicycle are connected, and that constrains the possible shapes of the track and how they relate. You can steer the front wheel in any direction, but the back wheel always follows a fixed distance behind. So how do you see that in the tracks? To get the essence of the idea of following a fixed distance behind, just experiment by pulling something. Back in the 1600s, this was demonstrated with a pocket watch on a chain. And I'll use this keychain flashlight in the same way. As I pull the end of the chain, moving my finger along a straight line, the mass follows a curved path, getting closer and closer to the line, but never reaching it. This curved line is called a tractrix. The track part comes from the Latin word for pull, as in tractor. Newton first derived its equation in 1676, and the straight line here is called the asymptote to the curve. The key notion we need from differential geometry is that of a tangent line. At any point of the tractrix, you can draw a tangent line. Then if you go forward along the tangent a fixed distance d, that's the length of the watch chain, you hit the asymptote. A bike moves in the same way because the motion of the back wheel is always aimed towards the position of the front, a fixed distance away. Now you can't push a pocket watch chain, they can only pull. So you actually miss half the tractrix if you just pull in one direction. The complete tractrix has two branches connected at a cusp. A bike frame can both pull and push the back wheel. So watch what happens as I move the front wheel along the line. The back wheel moves first along one branch, being pushed, then along the other branch, being pulled. Well, my bike track here isn't exactly on the prediction, but it's close enough to give the idea and show what happens at the cusp. I should tell you that to make this work, I chose the size of my tractrix so the distance from the cusp to the asymptote exactly equals the wheelbase of my bike. That's the distance between the points where the two wheels touch the ground. Then because it's a tractrix, the distance from any point of the curve to the asymptote, measuring along the tangent line at that point, is constant. Incidentally, this pushing aspect to half the curve means that the Latin track for pull is something of a misnomer here, leaving out half the fun. So maybe they should have come up with some better name for this curve, but we'll stick with tractrix. Now one reason the back wheel didn't exactly follow the curve is that the wheelbase of a bicycle isn't quite constant. Depending on whether a bike is designed for racing, touring, or utility purposes, frame designers carefully set the fork at an angle from vertical, and they set the front axle slightly forward from the steering axis. These factors determine stability and cause the wheelbase to change slightly when you steer and as you lean during a turn. But a simple mathematical model can ignore such real-world details if we still get good insight into what's happening. So for analyzing the bike paths, we'll just assume the distance is some constant d. Moving the front wheel in a straight line to generate a tractrix was just one special case of what a bike can do. Let's look at another case where you steer the front wheel with some periodic oscillation as you slalom down the road. The back wheel will follow, making a path with the same frequency but smaller amplitude. After the bike is gone, the back wheel track is easy to identify. It's the one with less variation. So given just the tracks, how do you know which way the bike went? You can first look to see which track has more variation. That's the front wheel. Here it's red. You can take any point on the other track, the back wheel path, and draw a tangent in one of the two directions to see how far it is along the tangent line to the front wheel path. If you choose the right direction, you'll find that it's the same distance no matter which point on the back wheel path you start from. But if the distance varies, you must have chosen the wrong direction, so try going the other way on the tangent line. In the direction corresponding to the motion of the bicycle, this distance is always the same, no matter which point you start from on the back wheel track. And if neither direction works, then Sherlock Holmes should be able to deduce that it was two unicycles who rode by. And then a mathematician sees one other case to consider. What if...
Okay, so let me just again mention one more time what he said. He said when we have something like that, the point is that the back wheel always follows the front wheel, right? Always. So if you look at their tracks on the ground, first of all, the first thing we want to understand is that which one belongs to the back wheel and which one belongs to the front wheel. The point is that because the back wheel always following the front wheel, the back wheel is the one which is kind of shorter and has less variation. So if this is the kind of traces of a bicycle, this is a trace of a bicycle, the blue one should belongs to the back wheel, the back tire, and the red one should belong to the front one, okay? Because it always is following the one on the front, right? So it wouldn't go as, it doesn't have as much as variation as the front wheel. And the other thing is that you should first suppose it goes right and then should suppose to go, it goes left, and test both of these cases. The point is that when the back wheel is here, if the bicycle is going to right, so suppose the bicycle is going to the right. If I want to find out where is the front wheel, I should draw a tangent line and see what is the intersection with the other curve. That would be the front wheel at that point. What is the front wheel at this point? I should draw a tangent line and see the intersection. This length should be the length of the bicycle. So if the length of the bicycle is D, this length should be D. Now, if our assumption is correct, this length shouldn't change. If I draw the tangent line here, this seems to be longer than D, and it is contradiction. The length of the bicycle doesn't change, so it doesn't go to right. Then we should try everything with the other direction, and definitely one of the directions should be correct. So, for example, if I look at the other direction, let me use two colors again. Okay, how can I make sure it's going to work? Okay, now let's suppose it goes to left, and then at each point on the blue one curve, if we draw the tangent, we find the front wheel. And the idea is that if we guess the correct direction, this distance between these two should be always constant. So you should first suppose it goes right, and then you should suppose it goes to left. And then at each time, you should compute the length of these tangent segments. And if it stays constant, it means yes, that is the correct direction. That's how you can find out the direction of the bicycle. So you can understand if the person who is committed like the murder in this story, if he was coming with the bicycle or he was leaving with the bicycle. That's basically the idea. Okay, so that's for that. Okay, so that's about curves. That was about curves. There are two important, these two subjects are very important, curves and surfaces. Well, what we saw was an example of curves, and we talked a little bit about surfaces. I want to talk a little bit more about surfaces. So what we talked about up to this point was kind of analytic approach to surfaces. I want to have a little bit more topological approach to surfaces too. It is related to a question in the exercises of the book. I want to elaborate a little bit about that. So topology is kind of like geometry. Topology is very similar to geometry. It deals with like shapes and figures and surfaces and curves and things like that. But everything is kind of extremely flexible, and you can deform everything any way you want. Things are not rigid, right? So for example, in Euclidean geometry, we have circles, right? They're perfect. They're very rigid. There is no way to bend them, right? In topology, we are allowed to bend this circle to get this thing, and it is still a circle for us. There is no difference between these two objects. Or even if we have a triangle, we can bend these like the sides and get something like this. It is still the same thing. And actually, these two things are equal in topology. Equals anything of the similar form. In topology, we are assuming everything is made of something which is completely flexible. We can deform anything in any way we want. And all of these things in topology are the same in topology. These things are all equal. Whereas in geometry, of course, circle is not the same as triangle, right? In topology, the things we can't do is we are not allowed to cut anything. So for example, circle is not equal to this thing. We are not allowed to cut this circle. We are allowed to deform, but we are not allowed to cut. Or we are not allowed to glue two things to each other, right? So for example, in topology, this cylinder is the same as this hyperboloid. One of them, we just pushed this part a little kind of inside, and we pulled the outer part towards outside. But in topology, they are the same. Whereas in geometry, they are different. We just saw they have two different equations. Okay. So for example, one thing they usually mention is so-called torus. Just the surface of donuts. Suppose you have a donut and just look at its surface, not the thing which is inside, only the surface, okay? The surface of a donut is called torus. We can deform this thing. For example, it's the same thing as this thing. That's a good question. Someone says in a topological sense, we are a donut. I don't think that would be true though, but that's something we can talk about. So in topology, these two things are the same. And usually people say donuts in topology, if you might have heard about it, is the same as a cup. Why? A cup looks like this. Well, in the sense of topology, this is the same as these two things are the same. They're equivalent. There is a deformation which takes one to the other one. Do you see that? Do you see a cup and a donut in the sense of topology are the same? Think about it for a few seconds. I want you to have a deformation in mind which takes one to the other one, deforms one to the other one. Oh, okay, I would take a look. Yeah, I guess Salvador Dali's paintings, everything is melting down, so I would agree. So, okay, I would show that to you now. Let's see why it's the case. Let's see why donut and cup are in some sense the same in topology.
Hi, my name is Henry Sagerman. This is Topology Joke. This is joint work with Keane and Crane. So there's an old joke in topology. So a topologist is somebody who can't tell the difference between a coffee mug and a donut. So topology is the study of geometrical objects when you don't care about lengths and you don't care about angles. All you care about is the sort of global shape properties. And so everything's made out of very stretchy rubber. And in particular, that means that if you take a coffee mug, you can sort of unindent the place where the coffee goes, and you can kind of squish out the handle a little bit, and eventually you can deform it into this perfectly symmetrical round donut shape. So, as the joke goes, the topologist doesn't know the difference between these because in the study of topology you don't care about any of these actual geometrical shapes of these different objects. As I say, this is joint work with Keane and Crane. He actually designed the shapes of these. I just did a little bit of editing to make them printable. Where do the shapes come from? Well, the thing you want to think about is soap films. So if you have a soap film, perhaps not in the shape of a coffee mug, perhaps in the shape of a bubble, and you poke on it a little bit, or you blow on it.
Okay, so I think it's kind of, the idea is kind of clear. If you look at the, these 7 objects here we have, you can see how continuously one is deformed to the other one, right? We kind of, here we have a cup, we kind of push down the cup, try to collapse it. And well, in the second thing in the cycle, we still have a cup. If you push kind of the bottom of the cup a little towards up, we get the third one. If we continue that, we get the fourth one. And then if we kind of make that thing a little bit more smooth, we get finally the torus. So there is a kind of continuous deformation of one to the other one. And whenever you can continuously deform one thing to another thing in topology, those things are the same for you. So for example, this torus here is the same as, is equal to, well, this one. You are allowed to deform things in any way you want, but it is not equal to sphere. And well, here torus has a hole. Well, mathematical term for it is genus. We say genus is equal to 1. It's the number of holes. Here, sphere doesn't have such a thing. So with continuous deformation, you cannot create or destroy a hole. So we say genus is 0. For example, another object would be a surface with genus equals to 2. It's like a donut, but it has 2 holes in it. And this is not equal to, it is not equal to torus. Okay, is it clear now what is the way we think about these objects in topology? Does it make more sense? Okay. Now, topology is a strange field in some sense. Let me start with a question. In the sense of topology, suppose we have an elastic body like this. It's kind of like, well, if we consider this surface with genus 2, this is equal to this thing. Does everyone agree? I'm just stretching it so I would get a neck, right? And one of the holes would be on one side, the other hole would be on the other side. Does it make sense these two things are equal in the sense of topology? And then I can make this one look like this, for example. And there is one hole here. There's this other hole. So all of these things are the same because I can deform one to get to the other one. No, this is not Klein-Bottle. This is surface with genus 2. I would mention Klein-Bottle. Klein-Bottle is also in your book. We would get to Klein-Bottle too. But now my question is that, is this thing, is this surface with genus 2, this thing, is this one in topology, is it equal to this other thing I'm going to draw for you? Maybe not, correct? Are these two things equal or not? That's the question. Suppose these things are made from extremely elastic things, and you can think about them as two, like the one way to think about it is that you can suppose you can just think about your fingers, right? And then your fingers are kind of separated like this, lock them like this. And the idea is that if you were Plastic Man, like it was in Marvel animations, if you could stretch as much as you want, could you somehow, without like along the deformation, your fingers should always touch each other? Was there a way to kind of do these things without like disconnecting your fingers to continuously get to this situation? Is it possible or not? That's the question. Okay, I'm getting a lot of no answers. No, we are not allowed to pass it through itself. No. We are not allowed to pass it. No, I just said like our fingers. No. We are not allowed to pass things from itself. Okay, I want all of you to think for 2 minutes. Just think, all of you. And I want everyone to give a yes or no answer. And let me decide how I want you to say yes or no. There is no fourth dimension. It's just a completely honest question. Can you do that or you can't? And think about for 2 minutes, and then we discuss it. Oh, I can make a poll. That's good. Okay. Think about the question now. We would decide about how to kind of either create a poll or something like that. We should think about the question. If you think the answer is yes, you should find a way to do that. And if you think the answer is no, you should find a way to say why the answer is no, right? It's math. You should find a mathematical way. You can suppose it's a question in the exam, you know? I want you to find a good reason for that. Do you have my voice? Someone just raise your hand. Okay. Okay. Yeah, good. Thank you. So okay, there's yes and no buttons here. For some reason, when I want to create a poll, it seems I should have made it before starting the meeting. It says your polling session is inactive. I'm not sure. Maybe I should change something in the setting. But you can just choose yes or no. I think there are two options. I think you can see that on both desktop and also on tablet, and probably if you're you're attending the class with phone, you can have yes and no. And if you can't do that, if you don't find it, you can just type yes or no. Okay, everyone, I want you all to answer. You have one yes, that's very interesting. Yeah, I would show you the sketch again. You should just wait for a second. Okay, so
You muted yourself.
oh, you have my voice now. Sorry, I'm using two devices. Okay, thank you. So 13 versus 12. Okay. Okay, let's see why the answer is no or yes. Okay, so let me draw them again. So one of them was this thing. That's one of these objects. And the other one was something like this. And the question is if these two things are equal or not, right? Okay. Yeah, it has genus 2. You're right. There are two holes. It has genus 2. Okay. Let's see. Let's try to kind of bend one of them to see if it would get to the other one or not. That's usually the idea. We should start to play around with one of them, try to stretch it, try to deform it, and hopefully we would get to the other one, or we should be able to show it's not, for some reason it's not possible, even though they are extremely flexible, right? Okay. Now, let's start with the left one, the one on the left side. I would erase this one here. That one is easy to remember, or I can just draw it here. Okay. Suppose I would put my finger here and I would push this part down, okay? What is going to happen is that this thing would deform a little bit. It would become like this, right? I can make this hole a little bigger, right? I can just push it a little down. It's a good question. Does this figure have 2 holes or 3? Is the genus equals 2 or 3? That's also a good question. We would answer that question too. I can keep on doing that, right? I can push a little bit more. It will become like this. I'm making this hole larger. And I can keep on doing that. I can keep on doing that. I can make this hole as large as this thing here. Maybe I should color it. So this is our surface. The surface is the red one. And in the middle we have this hole, right? I can make this hole even larger. I can continue this hole. I can make it as large as I want. Because it's topology, I can deform everything. Nothing is rigid, right? I can deform things any way I want, right? Now, I can push this thing up. I can push it up, right? So what would happen if I push this thing up? What will happen is that this thing will come just a little above. So it is like this. If I push it up, it becomes like this. Let's erase this thing. I can push this thing up, it becomes a little up. I just push that one a little up, right? It comes here, right? It's still fine, right? I can keep on pushing it up, but the point is that I can, okay, one thing I can do, I can continue doing is that I can use my hand, I can grab this part. So suppose I can grab this part with my hand from here. I can grab it and I can pull it up, right? What will happen if I grab it and pull it? I'm going to try to pull this thing out. What would happen? Well, this thing would continue go higher and higher, so it would move here. Well, it would first move here. Yes, you're right. So it would first move here, and then we continue to pull this thing out. So this is like this. If I continue pulling this thing out, it would go, this thing would go there, would be like this, for example. Okay, I hope my drawing is understandable. And if you push it a little bit more, it would completely go to the other side. This part here, if you push this thing inside, it would rotate. And we would get this thing going to the other side. So it would completely go to the other side. It would be connected to this thing. It would become like this. And then I can push this thing back down. As you can see, they are now free. There's this one here. And then this is this one, and then this one is this one, which is what we had here. So, oh, there's a video showing the same thing. We can take a look at the video. Let me see. So, so the answer is yes, they are the same. They are equal in topology, although it might look very, very, it might look like might seem to us that it's not believable. Ah, okay, yeah. Let's take a look at this thing. Seems to be good. Okay, yeah, that was very good. That was different with the way I explained, and it was probably even better. I had not seen that one before, so thank you. It was pretty good. That was pretty interesting. Yeah. So we saw it two different ways. If you want to, the way I used to explain this, I can show this one also to you. So if you want to see all of them in one photo, this is what I did. If we start on the top one on the left side, we pushed and made the hole bigger and bigger, and then we pushed that part on the second graph on the right side. We push that part up, and we finally get to the third one on the bottom, and that's the same as the surface with genus 2. Okay, so in the language of topology, these two things are equal. They are not different. For us, they are the same. Okay, so just one person was right. Who was right? There was just one person answered correctly. Who was that? Just introduce yourself. That's very good. That was very, very good. Did you see the answer, Adam, first, or did you answer, or that was pretty good. Okay. Okay, so that was the case. Let's look at one more example to understand this thing better. Let's see. Well, I should say something. Although these two things are equal, these two things are not. This is a problem in knot theory. Although those two things are equal, the union of two circles is not equal to a linked circle. Although you might think what we just saw would imply these things are also equal. We can even think about them as two donuts, and then two donuts which are, or two rings, and two rings which are kind of linked, or two donuts and two donuts which are, they are not equal. The point that they were connected was important. The fact that they were, these two donuts or these two rings were connected, it was important in this. We used this fact in this deformation. Okay. So I didn't explain why, but the first thing you can see that in a field named knot theory, which I wouldn't get into. One way to show these two things are not equal is with the use of a tool named fundamental group, which we are not going to talk about. But in the second thing, the second equality is correct. We can deform one to get to the other one, as you saw in my diagram, and also in the video. These two things are the same in the language of, in the sense of topology. Okay, so another question we asked was that what is genus? What is the number of holes here? Is it 2 or 3? Actually, the number of holes doesn't change when we deform. Here it's hard to see. You might say, well, there's one hole here, there's one hole here. There might be a hole here. Is it a hole or it's not? Well, it's hard to see that here, but we can actually look at that here. You can see there's exactly one hole here and there's exactly one hole here. So the answer is 2. The genus is equal to 2. The genus is something which doesn't change as we deform our object. It's called a topological invariant. Something which doesn't change as we kind of deform our object. Let's see another example, and then we continue. We would go to surface of rotation. The second example is something like this. Is these two things, are these two equal or not? How should I draw it? Well, we have this thing here. We have this thing here. This is 1. The question is if this thing is equal to this one or not. There's a question, is there any other topological invariants beside holes? In general, yes, many. But if you are, the thing which matters is for surfaces, the number of holes is, in some sense, the most important thing. So there is a theorem which says if we look at the surfaces which are, I haven't talked about that, but the surfaces which are closed, which means they don't go to infinity. So here, for example, we looked at the surfaces with 1 hole and 2 holes. We didn't look at the surfaces with, say, infinitely many holes, right? And the other thing was that our surface is so-called orientable. If you've seen Mobius band, you can go around Mobius band and go on both sides. It's another thing which I would talk later when we are talking about integral. This is important. I'm not going to talk about this now. You see that later. But if our surface is closed and orientable, genus is the only thing which matters, the number of holes. So the surface is either has 0 hole or 1 hole, or it has 2 holes, or it has 3 holes, and that's all which matters. Okay, but here the question is slightly different. Now here our objects are inside 3-dimensional space, and the question is that if we can deform one to the other one. Okay, so what is the answer? Okay, tell me, yes or no? Yes, you can, again, if you choose yes or no from the chat box, I would see the number of people who say yes and the number of people who say no. So either say yes or say no. Okay, so now a lot of you think the answer is yes, so it shows the power of learning. You have changed very fast. Can anyone say why? Does anyone have the answer? Raise your hand and then unmute yourself if you think the answer is yes or no, and then tell me why. Explain why. Anyone? No? Okay. I would explain. Oh, we already proved that the knotted shape on the right. Kind of, but now there is another extra thing going through these holes. You know, it might change that deformation is not going to work anymore, but very similar deformation does. So the answer is yes, we can make this hole larger like this, right? And we can continue doing that. So maybe it's better to draw a better one. We can make this hole again larger, like the previous example. Right? Now we have two bands. I would color the surface so we can see the surface better. Now you can grab this one and pull this one up, right? You can just grab that and pull that thing up. What would you get? well, this thing would go up. So it would go, for example, there. Maybe I should write slightly more careful. If I draw this thing up in this, so it would come if I grab this thing and pull it up. It would go. Well, it's first here. If I pull it up, it would go, for example, there. Okay, the sketching tool here is not good at all. It's very unfortunate. Okay, I would try to. Okay, it would go there. And then we can do that even more. We can keep on pulling this thing. It would go up there. It wouldn't go down anymore. And then if I just bring the rest down from here, I would get exactly what I have here. Maybe it's good if I show you the picture here too. So here you would see this deformation in one. First, we are in the first one. We are making the hole larger until we get to the picture on the right side, and then there are two bands. We can kind of pull those things up, and we get the third thing. And the third one is obviously, one of them is completely free, so it is the same as the thing we had before. Okay, does it make sense? Oh, the genus here. Well, here they are disconnected. It's kind of not hard to see. So here, there are two things here. So one of them is this thing, and the other one is this thing. So actually, when you want to think about genus, there are two different objects here. One of them is torus. The other one is this one. So genus of one of them is 1, the genus of the other one is 2. So here, genus is not something good, because the genus here is 2 and 1. Genus of what we have on the left side is also the genus of one of them is also 2 and 1. So genus can't tell us if we can so-called unknot two things, but the genus is 2 and 1 in both cases. Okay, so we should get to surface of surfaces of revolution. Maybe let's have 10 minutes break. Let's come back at 12:30 and finish this section. It's the last kind of surface we should talk about, the surface of revolution, and that would be the end of this section. So let's have 10-minute break and we would come back. So let me explain one more time. We are thinking about surface of revolution. The surface of revolution is built out of a function and one axis. We can choose any two directions we want. Here we've chosen y and z. So look at the z plane. I can take a function in that plane, y, z. I would take y equals z squared. Okay, look at this graph. The graph of y equals z squared is this one. This is the graph of this function, right? Then we should choose some axis. Let's choose the z-axis. And then we should revolve this graph about this z-axis like this. Okay? And look at the points when you revolve something around this z-axis. There are some points which this thing would cover, would sweep. It would be something like this. That would be the surface. That would call the surface of revolution of this function, y equals z squared, about z-axis, okay? Let's look at some other examples. Let's say here we take, for our directions, for our plane, let's say we take the xz plane, which is this plane, right, xz. Let's choose a function. Let's say x is equal to z. Well, this is, we can draw the graph of this function. The graph of this function should be in this plane, right? Now, we can rotate this graph around one axis. Let's say we take the z-axis here. If we rotate the graph of this function about this z-axis, we would get something like this. Right? If we rotate, it would look more like a square, circle, maybe. Better to draw it like this. And it would look like this. The answer would be this one. That would be the graph, which is the result of revolving this function along the z-axis. Okay. So the other thing is about the equation of these surfaces. What is the equation of this surface? Okay. So suppose we have a function in terms of y and z. So let's say finding the equation of the surface of revolution. The thing which matters in this case is the axis which we revolve about that axis. So for example, let's say we are going to revolve something about the x-axis. Okay, x, y, z, x-axis. So suppose we have a function y equals some function based on z, say f of z. This can be, for example, y equals z squared, or y equals 5z, or anything like that, right? So it's a function, something like this, y equals z squared in terms of y and z. We can revolve it, sorry, I made a mistake here. Okay, I should correct. If we are revolving about the x-axis, one of these coordinates should be x. So let's say y equals x squared. So this is the plane y and x. This is the plane y and x. Right? This one of them is y, the other one is x. Y equals x squared is something there, is something here. Right? It looks like that. If we revolve it around the x-axis, it would become something like this. Okay. Now I want the equation. I want to find the equation of this blue thing. The equation would be y squared plus z squared equals, well, I would make it a little more general. Rather than writing y equals x squared, I would write y equals f of x. It would be y squared plus z squared equals f of x squared. That would be the equation. So let me say in general, if we revolve about the x-axis, the equation would be y squared plus z squared equals f of x squared. If we revolve around the y-axis, it would be x squared plus z squared equals f of y squared. And if we revolve around the z-axis, the equation of the surface would be x squared plus y squared equals f of z squared. Let's look at one example. Let's see what it means. Suppose we have a function in terms of y and z. Suppose y equals 1 over z. Okay, so if you look at the yz plane, suppose this is y. Yep, I can go back for a second. These are the 3 equations, 1, 2, 3. Is that good? Okay, I can continue here. So the function, for example, so consider this function, y equals 1 over x. Okay, does anyone know what is the graph of y equals 1 over x on a plane in 2-dimensional space? How does it look like? Have you seen this before? If you haven't seen, I can explain that first. So, so maybe it's good to think about this one first. Y equals 1 over, yeah, that is correct. Y equals 1 over x. I want to know what is the graph of this function. One way to guess and find the graph of the functions is just trying different points, right? If x is 1, y would be 1 over 1, which is 1. So if x is 1, y is also 1. It gives us this point. If x is 2, y is 1 over 2, which is 0.5. So if x is 2, y is 0.5. Is here, right? We want to discover kind of the graph of this function. If x is 3, y is 1 over 3, which is 0.3. Somewhere around here. If x is 4, y is 1 over 4, which is 0.25. So if we connect these points, we would get something like this. What if x is less than 1? What if x is 1 over 2? Well, y would be 1 over 1 over 2. That's 2. So if x is 1 over 2, y is 2. Right? What if x is 1 over 3? 1 over 3 is here. Well, y would be 1 over 3. It's 3. So y would be here. So if we connect these points, we would get something like this. And it's not defined when x is 0. Not defined. Right? What about for negative ones? We can also try negative ones. Okay, I would erase these numbers we have here to look at the negative ones. What if x is negative 1? Well, y would be 1 over minus 1. It would be negative 1. So if x is negative 1, y is also negative 1. So we would get this point. If x is negative 2, 1, y would be 1 over negative 2 would be negative 0.5. So if x is negative 2, y would be negative 0.5. It's this point. If x is negative 3, y would be negative 1 over 3. So if x is negative 3, y would be negative 1.3. This point. So if we connect them, we would get something like this. This is y equals 1 over x. So the graph of y equals 1 over x is this one. This is x, this is y. It kind of looks like a butterfly, right? Okay. So now in 3-dimensional space, x, y, z. Suppose we have this y equals 1 over x. And suppose we are going to revolve it about the x-axis. Revolve around the x-axis. And the question is that find the equation. Let's first draw it and then find the equation. So we have this equation y equals 1 over x. Here, y plane is this plane. I would show it with blue. This is this plane. We should kind of draw the graph of this function here on this plane, right? It would be, look, it would be something like this. And then we need to draw it. We need to revolve it about the x-axis. It would become something like this. It would, maybe I would sketch only one part because it's hard, a little hard to see. It would be, it would be, it would be something like this. It's very hard to draw. It would be something like this. We had this thing, we had this graph, we are revolving that graph. Now the question is that, the question you might see in the exam is that what is the equation of this thing? Let's go to the previous page. Previous page. It says if you revolve around the x-axis, the equation would be y squared plus z squared equals f of x squared. Y squared plus z squared equals f of x squared. F of x is 1 over x squared. So the equation is y squared plus z squared equals 1 over x squared. That's the way to find the equation for these surfaces. Any question about this example? No? There is no question? Okay. Okay, so let's solve some problems about this section. I would give you some time to work out the detail of each one. Okay. Sketch the graph of the following surfaces. 1. X squared plus y squared equals 1. First in 2D. Well, in 2D it's not a surface, but first do it in 2D and then in 3D. Okay, think about this one for 2 minutes. Try to do it and then I would solve it. What is the type of this surface? The first thing we should recognize in these questions is that we should recognize what type of surface is this. What is the important thing about this surface? Yes, good. So in 2D, exactly, in 2D, it's circle with radius 1 with center 0, 0. In 3D, you should tell yourself there is no z here. There is no z. Whenever there is no z, when one of the variables is absent, it means it's a cylindrical surface. So if you look at x, y, z, in x, y, we have this circle. This circle comes there, and it is independent of z, so it's a cylinder in direction of z. That would be the answer. That is correct. So that would be the first one. Good. Okay. the second one. So first find the type and then try to sketch this surface. 4x squared minus 3y squared plus 12z squared equals maybe it's better shape, plus 12 equals 0. Find the type of the surface and then sketch the surface. Okay, think about this one for a few minutes. Okay, let's see how we should solve this one. The idea is that it's good here to divide everything by 12. If I do that, if we divide the equation by 12, we would get 4x squared over 12 minus 3y squared over 12 plus 12z squared over 12 plus 12 over 12 equals 0 over 12, which is 0. Now 4x squared over 12 is just x squared over 3 minus 3y squared over 12 is just y squared over 4, and 12z squared over 12 is just z squared, and 12 over 12 is 1. So we would get this equation in a slightly simpler form. Now, I would move this one to the other side, I would get -1, right? If I move this +1 to the other side of the equation, we would get -1. So x squared minus y squared over 4 plus z squared is equal to -1. If I multiply everything by -1, left side would be minus x squared over 3 plus y squared over 4 minus z squared. The right side would be equals 1. Okay, see, there are 2 negative signs here and 1 positive. If we go back and look at the, you can, if you have the book, you can look at the table in the book. In the edition I have now, it's at the page 814. There is a table in section 11.6, which has all these surfaces. We can look at which surface has 2 negatives and 1 positive. And we would see it's going to be the 2-sheet hyperboloid. So it would be hyperboloid of 2 sheets. So it would be always in direction of the one with positive sign. So if here we have x, y, z, these 2 sheets are in direction of y. It means it's going to be kind of like this. Right? We can try to write down in terms of z. Z squared would be, in order to sketch it with computer, we can write it in terms of z. Z would be 1 plus x squared over 3 minus y squared over 4. If we take the square root of it, it would be plus minus the square root of this thing, right? We can use this thing to sketch the graph of surface. So let's do that. So what is z here? Okay, we need 2 functions, right? And what was the equation? Z would be x squared. Well, it would be y squared over 4. Z would be y squared over 4 minus x squared over 3 minus 1. Am I right? It might not be right. Well, we would understand what's the problem. Okay, I made a mistake. So z squared would be y squared over 4 minus x squared over 3 minus 1. Z squared would be y squared over 4 minus x over 3 minus 1. What's the mistake I made? Oh, the squared root. Thank you. Thank you very much. It's z squared. Z would be square root of that. Okay, it doesn't draw it anymore at all. What? Okay, because there is nothing in this region. Maybe if we look at from minus 10 to 10, we would see something. And here minus 10 to 10, minus 10 to 10, and then if we go a little away, yeah, that's our. There are 2 sheets of hyperbola here in this picture. Okay. Okay, so that was it. Let's look at another example. Find the type and sketch this surface. Y minus y squared minus 4z squared equals 0. Think about this one for a few minutes too. So first find the type of this surface and then sketch the surface. So here, x minus y squared minus 4z squared equals 0. It means x is equal to y squared plus 4z squared. So this is the other type I mentioned, which one of the variables is not squared anymore, but the other 2 variables are squared, right? And this is I think not the last one. This is the elliptic parabola. So we have our variables x, y, z. It would be something in direction of x, something like that. But the cross section is not going to be a circle. It's going to be an ellipse. And this ellipse would be more extended in direction. Well, if we divide everything here by 4, I would get x over 4 is y squared over 4 plus z squared. It would be extended more in the direction which has the larger no, it's not saddle. Remember, in the saddle, one should be positive, one should be negative. If it was y squared minus z squared, it would have been saddle. When it's plus, it's elliptic paraboloid. So it would be more extended in the direction of the variable which has larger denominator. So here y squared. So it would be like this, but it's more extended in direction of y rather than z. So it would be something like that. And we can try to, so here z would be equal to, if we want to sketch it with computer, z would be equal to x over 4 minus y squared over 4 square root of that, plus and minus, right? Oh, it is extended in direction of x, that is correct. But if you look at one cross section, what will you see? You would see an ellipse, okay? There are, well, I mean, if you look at the ellipse in the cross section, there would be y direction and it would be z direction. Now I want to see how does this cross section look like. I told you, look at these numbers in here in denominators. One is 4, the other one is 1. one is 4, the other one is 1. So this ellipse is kind of, it's not a circle, definitely. It's an ellipse, but it's longer in the y direction. It goes more in the y direction, okay, rather than in the z direction. If it was, for example, so maybe as another example, so x equals y squared plus 4z squared would give us x over 4 equals y squared over 4 plus z squared. This one would look like this. But if the equation was like this, was 4y squared plus z squared, if I divide everything by 4, x over 4 would be y squared plus z squared over 4. Now here, this number is larger. So it would be more like this. Let's look at the graph. Let's try to sketch the graph with computer. It doesn't matter, that these subtleties doesn't matter much, but I want you just to at least see it once. So let me share my screen with you. So here z would be either plus or minus something to the power 1 over 2. What is that thing? That thing is x over 4 minus y squared over, well, one of them over 4. Let's say, yeah, 1 over x squared over 4. That's one of them. The other one is minus that. Okay, we are very close to this surface. And probably if we change these to 2 minus 2, 2, and this one to minus 2, 2, minus 2, 2, we would get a better, sure, okay. So this is z, this is y, this is x. See, it's extended in direction of x, that's definitely correct. Can we even make it smaller? So if we look at this thing, why one side is different with the other side? That's very strange. Anyway. I'm not 100% sure. Maybe I'm making a mistake. Okay, I would go back to our question, Maria Anderson. But let's just look at this thing. So here, if we look at this, it's extended in direction of x, but as you can see, it's different in direction of y with direction of z. It's like an ellipse, not a circle. Yeah, why does it, why is this thing not completely, why one side is different with the other side? You have used maybe, oh no, let's try again. I have no idea. So the idea, so let's go back. So the idea is that in this example where here x is equal to y squared plus 4z squared, it means it's something in the direction of x. But this thing in direction of x, you can look at this cross section. Is it a circle or it's an ellipse? The answer is this thing is, if you want to find out what that thing is, you should look at this part. You should look at this part. And whichever of these two things, which has a larger coefficient, for example, here the coefficient is 4, here the coefficient is 1. It means the radius in direction of z would be smaller than the radius in direction of y. So if you have 4 here, the radius in direction of y, for example, would be something like 1/4. In direction of x, it would be 1. So it would be something like this. Anyway, it doesn't matter much for our purpose, but it's good to know. Yeah, I'm not sure why there was this bug there. Okay, let's look at one more example. Let's look at this one. X squared plus 2y squared plus z squared minus 4x plus 4y minus 2z plus 3 equals 0. So what type is this? And then sketch the surface. So we can change the equation and write it in slightly more standard way. So here we have, let's first of all collect similar terms next to each other. We have x squared minus 4x, right? X squared minus 4x. Let's write down these two next to each other. We have 2y squared plus 4y. Let's write down these two next to each other. We have z squared minus 2z. Let's write down these two next to each other, and then there is plus 3 equals 0. We can complete this square. Yeah, that is true. So x squared minus 4x, we can write it down as x squared minus 4x plus 4 minus 4. 2y squared plus 4y plus, what should I add here? Here I should add plus 2 minus 2. And I have z squared minus 2z plus 1 minus 1 plus equals 0. Okay. What is the first thing? The first thing is x, yeah, you're right. Your answer is correct. So the first one is x minus 2 squared minus 4 plus. The second one, I can, well, forget about this part, minus 2 part. Look at 2y squared plus 4y plus 2. I can factor 2 out of it. It would be y squared plus 2y plus 1. But what is this thing? Y squared plus 2y plus 1 is y plus 1 squared. So instead of this thing here, I would write y plus 1 squared. Minus 2, there is a minus 2 there. And finally, the last thing is z minus 1 squared. Minus 1 plus 3 equals 0. Okay, look at these constant numbers. Minus 4, minus 2 is minus 6, minus 1, negative 7. Negative 7 plus 3 would be negative 4. So I can add all these constant numbers. I would get minus 4. Okay. I can take minus 4 to the other side of the equation. I would get x minus 2 squared plus 2 times y plus 1 squared plus z minus 1 squared equals 4. Now, I usually like to have 1 here on the right-hand side, so I can divide everything by 4. It would give me x minus 2 squared over 4 plus y plus 1 squared over 2 plus z minus 1 squared over 4 equals 1. Okay, just like sphere, these numbers here, they give us the center of this thing. First of all, this thing is an ellipsoid, right? This is an ellipsoid. And then we can find the center of this ellipsoid. The center is we should write it as x minus something, for example. So here is x minus 2. So if you look at the center, the first coordinate of the center is 2. What is the second coordinate? The second one is y plus 1. Remember, it should be y minus something. Plus 1 is the same as minus 1, right? So the second component of the center is minus 1. And the third component is 1 because it's in minus 1 square. So this is the center. So center is 2. We come forward in direction of x by 2. Minus 1, we go in direction of 1. Negative direction of y by 1, and then we go up by 1. This is the center of this ellipsoid. And then we should kind of know how does this ellipsoid look like. As I said, it's more extended in direction of the components which they have larger denominator. So it's more extended in direction of x and z, and less in direction of y. So it should be kind of, well, it's hard really to sketch, but it would be something like this. In the y, it's kind of like that. In order to see it better, we can sketch it here on computer. It's really kind of close to a sphere. It's hard to see. I mean, it's like a sphere which is extended in one direction slightly. It's kind of like the Earth. You know, the Earth is not also completely a sphere. The Earth is kind of also an ellipsoid. It's more extended in one direction. But if you really look at it's really close to a sphere. It's really hard to see that it's not in a sphere. The Earth is also very, very, very close to a sphere. So we can see that if we look at the images we have from Earth. If we look at the images we have from Earth, we would see that Earth, although it's really not completely a sphere, but it's very close to a sphere. Earth is also an ellipsoid, but it's an ellipsoid which is very close to sphere. So you can look at this, for example, or you can look at this. It's really, really close to a sphere, but it's extended in one direction. Does anyone know in which direction it extends and why that's the case? Why it's not really a complete perfect sphere, why it's an ellipsoid rather than a sphere? If you know the answer, unmute yourself and say the answer. Okay, if you don't know, I would. Rotation force, that is correct. So yeah, we got a few answers, that is correct. So that is correct. So you can think about it. Maybe I shouldn't say the answer completely, but if you have something which is even a perfect sphere, okay? Suppose it has an axis, a direction, an axis, say show it with z, which it rotates along that axis, right? So say here is North Pole, here is South Pole, and this sphere is rotating about this axis. Suppose it's rotating very fast. It would slightly change. The shape of this thing would slightly change. And it's good to think about why and how it changes. I wouldn't give you the answer now. You might have heard this thing before. If not, you can think about it a little bit. There are things in physics which they should stay invariant. And when you rotate this thing, the invariance of those things would imply this sphere would slightly change. Okay, let's look at another example. Z equals y squared over 16 minus x squared over 16. Type, and then sketch. Think about it for 1 more minute. Yeah, that is true. The answer is, well, either saddle, or we call it hyperbolic paraboloid, or saddle. And well, why? First of all, remember when here the degree is 1, not 2, and one of these have positive sign, the other one has negative sign, we are dealing with saddle. And if you look at the axis, x, y, z, it's going to be a saddle in direction of the negative. Well, in direction of, it's kind of like, well, let me show it to you. So here, if y is the one which is positive, it would be in direction of y, it's going to be like this. And if x is the one which is negative, in direction of x, it would be like this. So this saddle would kind of look like, this thing. So remember, here y is the positive direction. In the positive direction, we have something like this. X is the negative direction. In direction of x, we have something like this. Okay, that's how to sketch these saddles. Okay, that's it for today. We finished this section about surfaces, and but this is in the direction of x, right? Well, there is no in direction of for saddle actually. It's going to extend in all directions. It goes to infinity in all directions. Okay, that's it for today. Any question? Where to draw the parabola? On which axis? The parabola is on the YZ axis. Well, if you look at x equals 0, you have YZ plane, right? There, x is 0. So there you have z equals y squared over something, over 16 here. So that's on YZ plane, the positive parabola. The negative one is on XZ plane. Okay. Any more questions? Okay, that's it for today. I have office hours on Monday. If you have any question, you can just come and ask me. Okay, I would upload the videos and the homework and the notes today or tomorrow. Okay. Okay, see you soon. Goodbye.